So let's start with eigenvalue decomposition. There are some limitations. For one thing, we can apply this only to a square matrix. So in our case, for computer science and data science, our matrices are not going to be square. It's going to be horribly non-square, and we cannot apply it. The basic definition of eigenvalue decomposition or eigenvalues and eigenvectors is that A times an eigenvector is an eigenvalue times the same vector. So it's a scale version of the vector that results from the transformation implemented by the matrix A. Now if you arrange these vectors in columns of a matrix S, and if you arrange the eigenvalues as the diagonal elements of another matrix, then we can rewrite this definition as a matrix equation A is equal to S lambda. This is always true because that comes from the definition. It is true by definition. Now on top of that, if we know that S is invertible, which means that we have enough eigenvectors that are linearly independent, in that case we can invert it and then we can write A is equal to S lambda S inverse, and that is eigenvalue decomposition. And this works especially well for real and symmetric matrices because we are guaranteed to have eigenvectors that are orthogonal to each other. Then you get an orthonormal matrix. We typically call that Q, and its inverse, which takes the place of S inverse, would be just a transpose. That is a property of orthonormal matrices. So we can write A is equal to Q lambda Q transpose, which is the spectral theorem. So eigenvalue decomposition, A has to be square, it has to be real, and A transpose is equal to A, it has to be symmetric. So that's when we have good eigenvalue decomposition of the kind in the spectral theorem. But for any general matrix A where it is not square, it's got m rows and n columns, we would like to have a similar decomposition that has the same form. So we would like to write A is equal to U, some matrix, some orthogonal matrix, orthonormal, sigma, a matrix that is diagonal, and V transpose, where V is an orthonormal matrix again. U and V are orthogonal, sigma is a diagonal matrix. So this is pretty close to the spectral theorem. It's just that instead of Q and Q, you have two different matrices. That's probably okay. So close enough to a spectral theorem. This is what we would like to have. Now notice that sigma here is not a square matrix. U and V are square matrices, but sigma will have the same size as A. If you can decompose any matrix, especially a data matrix, then what we will get is the sigma matrix. It's got main diagonal elements, non-zero, everything else is 0, but it's the same size, m rows and n column as the original matrix. So lots of zeros inside, and U is an m by n matrix and V is an n by n matrix. Soon we will see that it can be made smaller by considering that A has a rank of R, then only R values inside sigma will be non-zero. So we can actually take a small R by R and we can call that sigma hat. So it's a small version of a sigma. And in order to make the multiplication work, then U will turn out to be a non-square matrix. So that is not an orthonormal matrix yet. It's got columns that are actually orthogonal, but not a square matrix. So it's not an orthonormal matrix. So now let's just look at how the multiplication works. In the case of full SVD here, I have n by n here. The transpose of that will also be n by n. This n and that n will cancel off. So this product is going to be m by n. And then this m and this m will cancel off. So the final product is going to be m by n, which is the size of A. And in the case of the hatted version, what we will call economical or smaller SVD, I have R by R inside. V is n by R. So V transpose is going to be R by n. So this R and that R will cancel. And this R and that R will cancel. So what is left would be m by n. So that also works. The dimensions actually work out fine. So hatted version is called the smaller economical version. But it's important to know that this economical version is not an approximation. It's not an approximate equation. It is still completely accurate. Now let's take an example. So let's look at a matrix that's got same elements in the diagonal and one off diagonal element. This is actually very similar to a shear matrix. What it does is pretty much identical to what a shear matrix would do. It's a triangular matrix. What are the eigenvalues? It's got two eigenvalues. They are the same. Square root of 3 by 2 because those are the diagonal elements. Determinant will be this guy times this guy minus this guy times this guy. That is a 0 because there's 1 0 there. So it's going to be that. And that means I have square root of 3 by 2 as the eigenvalue appearing twice. The eigenvector is 0, 1, and that happens only once. So it's got algebraic multiplicity of 2, geometric multiplicity of 1. So this is not diagonalizable and is a shear matrix actually. And this is a bad situation in eigenvalue decomposition. We will get stumped here. We would have to stop. There's nothing more we can do here. But SVD, we can actually perform on this one. We can write this matrix as sum U times a sigma times V transpose, and it will turn out that that is the way it is. U is a matrix like that. That is a orthogonal. It's actually a rotation matrix. Sines and cosines of angle 60 in there. And sigma is a scaling matrix. So V transpose is another rotation. If you look at V transpose, that is a rotation through an angle 30, and sigma is a scaling. It scales the x values by 1.5, 3 by 2, and y values by half. So that's what it does. And U is a clockwise rotation through an angle 60. So let's start looking at these things. Here we are actually dealing with a 2 by 2 matrix so that we can visualize this in R2. But in general, it doesn't have to have the same number of rows and columns. It could be something that takes vectors in R2 and gives you vectors in R3 or R4. So shear matrix, what it does, it takes the first unit vector, the first column of the identity matrix, and gives you a transformed version of minus root 3 by 2 minus 1. That is the first column of the shear matrix. And the second column says that it will take the second unit vector 0, 1 and will give you a transformed version Q2 triple prime to be that. And if you look at it, what it does to Q2 is just a scaling. It makes it a little smaller but in the same direction. So that is actually an eigenvector with the eigenvalue square root of 3 by 2. What it does to a unit square, if you think about it, is to transform that into this parallelogram. So it is like shear. It squashed the unit square a little bit and then sheared it downward. But instead of a pure shear, it also scaled it by a little bit. So it's a scaling and shear, but a shear matrix nonetheless. Now let's think about the decomposition. A is equal to U sigma V transpose. So V transpose will apply first. So that is a rotation. What it does to a unit vector along the x-axis is to rotate it counterclockwise by 30 degrees. Does the same thing with the other unit vector, the blue one, so 30 degrees. And the matrix is what it does to the unit vectors. And you can just write down the matrix. Actually, it was given to you is square root of 3 by 2 half minus half square root of 3 by 2. And that is actually a rotation by pi by 6, 30 degrees counterclockwise, which means all the vectors whose tips fall on this unit circle will get transformed to other vectors whose tips still fall on the unit circle but at different points. So all the vectors in the first quadrant between here and here will end up between here and here. The next one is a scaling. So what it does is to take the first vector q1 and scale it up by a factor 1.5, and the second unit vector gets scaled down by a factor half. So it basically takes a unit circle, squashes it vertically and stretches it horizontally. Now if you think about the vectors that got rotated by V transpose, they are like the shadows of the vectors here and here, and they get squashed down to this point and this point. So in the original quadrant, everything that was between here and here in the unit circle now are on the ellipse. The tips are on the ellipse between this point and this point. So that's what's happening to those vectors. That is the action of V transpose followed by sigma. There is one more rotation that is coming up, clockwise rotation, that takes this vector q1 and rotates it and brings it along this major axis of the ellipse. So it takes the whole ellipse and rotates it down by pi by 3, which is 60 degrees in the clockwise direction. So what that means is that my original vector that was q1 that got transformed to some other rotated version and then squashed down to this shadow of the red vector here, that is now going to end up here because the whole thing got rotated, and that angle from here to here, that is 60 degrees. Similarly, my original q2, which went somewhere here on the unit circle and then squashed down to this point here, and that gets rotated to this point so that it ends up back on the y-axis. Now if you think about it, in the original unit circle, the vectors whose tips were between this point and this point in the first quadrant, now their tips are going to be between this and this. So that is the action of the matrix A, now decomposed into 3 different matrices, and if you multiply all 3, surely you're going to get A back. So that's what the decomposition does and tells you. The vectors whose tips were on the unit circle there are now with their tips on the ellipse here, the pulsating ellipse there. Now, just to summarize what's happening here, if you just apply blindly just A matrix directly and try to figure out what it does, it takes the unit vectors and then gives you some ellipse as shown here. And if you decompose it, then you can see that it's actually a rotation followed by a scaling and then followed by one more rotation. Much like what we saw in the spectral theorem interpretation of a real symmetric matrix, but this is for a general matrix that cannot be diagonalized. Now remember, this is a 2 by 2 matrix A, but it doesn't have to be 2 by 2. It could be m by n. So it would take a vector in Rn and take it to some other space Rm, but still it's going to actually end up on an ellipsoid, and singular value decomposition will tell you the properties of the ellipsoid. So it's much more general than EVD. Now let's